Okay, I'm going to talk about my project. This is a quantum neural network based correlation for frictional pressure drop for non-azeotropic mixture during cryogenic force boiling. This project is based on another project that I have with some colleagues, and we try to do an artificial neural network with the same principle. And in this I want just to try what happened if I try to do this with a quantum neural network, and what is the architecture that better give me results about this project. Okay, um, like this kind of correlation is a thermodynamic correlation that we use when we have heat exchangers with microchannels. I am a mechanical engineer and I have some expertise with this, and we found some experimental results about this process, and that those experiments were compared with correlations and were not so good, like 20 to 30% of error. And we did this with an artificial neural network, and we reduced the error to 9%. And in this case I just used the same experiments that are here in these tables. The first is just some components, and we are changing the components. In this we have nitrogens, like is the difference between these two, and this just have the first two components, and I think that is methane and something else. But yeah, those are the experiments that we are going to use to try to create a quantum neural networks. And okay, I first load the data. It's like almost 4,000 data points with 4 inputs and 1 output. The 4 inputs are um, the flux mass, the Reynolds number, the quality, and the frictional factor. And what we want to try is just create a quantum neural network that could give me a correlation of this process and get at the output the pressure drop. Okay, I tried different architectures, and the one that better gave me better result is this one. When I use strongly entangling layers with like a dip of 3, and I repeat 3 times this layer, and also I found that encoding the input, if I just use one input and like 3 times this strongly entangling layer, I just lose the information of my input, because I am trying to put this information at the beginning of the circuit, and we are like losing that information through all the circuit. Then I try to change this, and each time that I apply this layer I also reapply the input, and this is like the architecture that better result gave me. I'm not completely sure if it's good or not, but I try other less entangling layers from the templates, and neither of them gave me these results. Then I decide to use this kind of layer, and I train with different number of layers and the deep and different number of qubits, but just this architecture is like the best that I could find for my correlation. But yeah, I also try to apply a different like encoding the input, but I couldn't get better results. Okay, this is for the layer. I just and I also use mini batches, and this improve significantly my circuit, and the optimization process. Okay, and I call here the circuit. I just use the cost function, like the square of the difference between the output of the circuit and my pressure drop. Here the output is between -1 and 1. Then I have to translate this into 0 and 1 because I normalize the pressure drop. And I changed the batch size, and 75 was something that gave me a better result. I reduced the learning rate, and yeah. And here if I want to load the parameters, some parameter that I have before, and I want to retrain, or use some parameters and not a random number, then I can load those parameters here. And yeah, these three values of here is just to, if I want to check if I am learning. If not, sometime I have to stop. And I am doing a test. I am using a test, some values not used for the training, to validate my model and to see if my model have overfitting. But yeah, like both values for the training and the test keep like the same, in the same way. Then and I printing this like every 5 times to see how this is behaving. And the result, then I compare with the experimental result and see if some of the experiments, here are the experiments that I took for the training, what happened with those experiments. And what I get is not what I was expecting. I was thinking that I had an improvement in the error, but the reality was that I was getting like not the best performance if I compare this with the artificial neural network. Even this is like in a mean square error, no, a mean relative error. I have like 32 for the QNN, and for the artificial neural network was just like 9% for the whole bunch of cases. Okay, and I have here different set of experiments. Some are better than others. For the first set of table 1, I get better result than for the other 2 tables. And I think that is because I have more cases here. And for the other, I don't have enough cases to really learn a lot. And yeah, here like the A, B, and C are good, not at the extreme, but at least is better than the others. Okay, and here I am error bar of the mean relative error for different cases, and for the cases that use that are in table 1, this is a better training than in the other cases. And yeah, I have here the mean relative error of 37.4% with respect to the to our target value. Okay, I have to explore. My conclusion are that I have to explore a different architecture, because I think that I am missing something that is crucial for getting good results, because I have more parameters in the quantum neural network than in the artificial neural network, and I am not getting better results. Then I have to check that. Thank you so much for such amazing quantum hackathon, to the whole team of Penny Lane.